as I have already been introduced, my name is Stupazzini, and I work for the Munich Re company. Re actually stands for reinsurance. In a nutshell, we are insuring the insurance company. And by the way, actually, you are presently sitting in an area where Munich Re was already present more than 100 years ago during the famous 1906 event affecting San Francisco. So it's a long story, I would say. And I hope that during my presentation is going to be clear at a certain point why someone coming from the reinsurance sector seems to be so much interested about the physics-based simulation. Let me very, very shortly comment on that. The first thing is that I dedicated quite some time in the first part of my professional life to the development of a code that, thanks to the presentation of Roberto Paolucci and Chiara Smerzini, has already been illustrated. And in 2009, I actually joined the Munich Re company. And in order to understand a little bit better what I'm doing inside the company, let me just sketch very shortly let me illustrate this sketch. As you can see, traditional insurance is typically working with a certain indemnity-based contract. It means that is defined a certain cause of loss, for example, an earthquake event. And then out of that, you will get basically losses on your facilities, on your assets. And what is going to happen is that after a certain loss adjustment process, you will get payment. This basically implies that my duty inside the company is the one to provide and calculate a technical net premium that in a nutshell means estimating the frequency of the different possible claims and the expected amount of each claim. It sounds somehow simple, but it is clear already that for certain field of the insurance sector, these can be mostly based on empirical data. Let's think about the automotive sector. It's pretty clear that you receive every year a certain amount of data. And if the situation does not change, you can proceed with this kind of so-called burning cost method. That is a sort of, I would say, elementary estimating of forecast method, unless there are some kind of technological changes, like, for example, the idea of having autonomous drive that obviously will change quite dramatically this situation. In our case, specifically the natural catastrophe field, what it happens is completely different, because actually we cannot count only on empirical data, since we do have a very few of them, and in most of the cases it's also relatively difficult to try to extrapolate from a different historical time and then to have a reliable picture about what would have happened today. So in a nutshell, what we end up is a relatively difficult situation where we do have just one point illustrating how often it happens, a certain amount of loss, but what we would like to get is in a nutshell a curve. And so here where it comes actually the link between our two words is that we want to determine what is the frequency of those losses, and we don't have enough empirical points. So basically what we typically do is taking advantage of the property catastrophic modeling. And I assume that basically since the theoretical development of this kind of method during, let's say, the first half of the 70s, and then in the 80s, there was a very important development of this kind of property catastrophic model. And what I'm going to illustrate you is the way and the shape that we're going to use inside our company. And typically what we do is Monte Carlo simulation, as it was already previously mentioned. It means in a nutshell that what we are really applying are a scenario or a footprint. I will use basically the word as kind of similar synonymous. And here you see just illustrated in the area of Chile, two of that example. Please take also into account that obviously the colors refer to the different shaking, and the points basically are representing the distribution of a potential portfolio all over Chile. Now, what happens is that in order just to get a little bit more in detail, in property catastrophic modeling, one of the keywords is event loss table. That is relatively simple to illustrate it. We have just a long list of event ID or loss ID. Each of them, it's basically associated to one of the footprints that we have seen before. And you have to imagine that inside one of these modeling, we've got hundreds of thousands of these potential scenarios. Each of them obviously determine a certain amount of loss that I will illustrate a little bit after how it is done. And then finally, we have associated to add a probability. Now, if you got these three columns, in a nutshell, it's done. Because the one thing that you have to do is just simply sorting the losses, basically from the highest losses to the lower one. And the other thing that you can do is just simply multiplying and accumulating basically these losses time probabilities and getting basically the average annual loss. That is nothing else than the technical premium that you have to request every year in order just to fairly price this kind of risk. Now, why I was mentioning about the sorting of the losses, because as you probably remember at the beginning, I was illustrating a plot where there was the return periods and the losses, and the curve that everyone in our sector want to get is the probable maximum loss. Actually, this curve has a different name. You can look at the literature. But in a nutshell, what you will get is just that these curves, it has been created exactly out of the event loss table. And each of that point can be basically associated with a specific scenario. So, having said all of that, in my presentation, I will essentially focus on some important keywords that I think that deserve a little bit more of understanding. One is the ground motion models, the second is the portfolio, and the third one is going to be the spatial correlation. Let's start actually from the ground motion models. Obviously, there are incredible benefits, at least for us, in using ground motion models. But the first one is, as you can probably already imagine, we are talking about hundreds of thousands or million nowadays of scenarios that need to be calculated, and in many cases they are also calculated on the fly according to the portfolio that you have. This requires a certain computational cost that we cannot neglect, and so it's extremely practical to have a function that in fraction of a second on normally nowadays on each and every laptop can compute this footprint. The bottleneck, the X, has been already illustrated by many yesterday. One of the things that probably puzzled the most the people that are using this kind of very nice tool is the fact that in the field, in the region where we would like to have data, because they are really responsible for the damages, in reality we know that we are collecting not as many data as we would like. And so it basically means that we are also sparsely sampling where we would like to have a better picture. And it's also relatively unlikely, even if we cover of an incredible dense network of seismometer, to get just right away in a specific area of the world the data that we would like to get. Because earthquake just simply happens, luckily, rarely. And the other side, what you will see is just other kind of phenomena that we all know that are difficult actually, not impossible, but difficult, I would say, to model properly with this kind of relatively simple ground motion models. Here you see this spectacular picture in the counter station and the resonance. Nowadays, actually, we all know that this kind of phenomena and this kind of complexity can be tackled. And here it comes for the first time the physical perspective, so that in reality what we are observing is a very physical phenomena. And in the last, I would say, decades, there were impressive improvements in terms of tools and high-performance facilities in order to have more and more reliable simulation out of this physical frame. So it was already illustrated, so I will definitely not go into detail, but as you already have heard, in order to provide physics-based scenarios, what we need is to have basically verified and validated tool on the one hand. On the other, you need actually a certain framework that allows you to accomplish the task of having this calculation done within a given time frame, I would say as fast as possible, and with the required quality. Furthermore, at least inside Polytechnico, there are certain constraints about where we do rely on that kind of seismogram. Therefore, we were just setting up a certain recipe in order to have also the high frequency component. I heard from previous speaker that nowadays it looks like that the threshold is getting higher and higher. I'm very glad about that. And nevertheless, we all know how CPU time consuming is just to increase with the frequency, and what are also some kind of drawbacks or limitations. So what I would like to stress out is actually I always like to recall this one-page paper of Hausner that has been written just almost after the famous sequence that was affecting Turkey in 1999. Actually, it was asked Hausner to have an estimation about the losses and the casualties related to that event. And he was very wisely saying that magnitude and epicenter do not provide sufficient information to engineers. And at the end, he was also commenting something that, in my opinion, is enlightening. For a large earthquake, the epicenter is not as helpful to engineer as it is the footprint. And this is exactly the reason why we decided to name, out of that communication, what I'm going to illustrate now as footprint-based PSHA, probabilistic seismic hazard analysis. Let me just highlight or underline the fact that typically there is a kind of confusion worldwide about the fact that someone that is doing physics-based scenario, also renamed as deterministic scenarios, is also then doing some kind of deterministic seismic hazard assessment. Actually, in my opinion, this is completely wrong. You can definitely use a physics-based scenario within a classical probabilistic seismic hazard framework. And this is exactly what we were illustrating a couple of 3 years ago in this publication, in which, as you can see, in this schematic sketch, you will see that basically we were introducing a certain part of the logic branch, the logic tree, with certain branches associated as typically is done with Graham motion prediction equation or Graham motion models. And then there are other branches also with certain kind of weights that are directly associated to the different realizations that we have done with a physics-based simulator. These, in my opinion, it was extremely interesting, and let me highlight a little bit what are the outcome of something like that. If we use Graham motion models, as we already say, there are incredible pros, not only in terms of computational efficiency, but also that you are using real observed data. There are certain kinds of limitations. Nevertheless, what it happens is, if you take into account a certain kind of, a certain area with 4 different stations, let's say, you will see in a nutshell that given a certain magnitude, certain distance and soil, you will get obviously the Graham motion median prediction, and then a large variability of what is the Graham motion there. If you introduce the physics-based scenario, the very nice things about it is that on the one hand, you introduce more complexity, but also and especially, you will get basically the spatial correlation of your ground motion because it is directly physically modeled. And this is an incredible asset for someone like us that need always to face the challenge of properly determining what are the losses to a portfolio to a distributed amount of risk located on a certain area. And so you can do one simulation, and obviously you have to think that those stations are related then to different kind of buildings with different aids, different construction year, different construction material. And so my duty inside the company is basically the one of providing the losses associated to the different building, and out of that, cumulating the losses and having finally a loss per event. This basically recall the concept that I was just explaining at the beginning about the event loss table. So this is one event with accumulated losses per event and with its own given frequency out of the logic tree and all the assumption in a standard framework. So the next step, it would be essentially nothing else than having another different realization. And as you can see, not by chance, I was just selecting something as an anti-directive rupture. And you will see that the losses would be definitely lower, different from what we've seen before. But again, I don't have to reconstruct a posteriori the special correlation of the ground motion. This is intrinsically done in our physics-based simulation. And so after something like that, in which, as you can imagine, now we are jumping in probabilistic risk assessment, basically, we will get basically a long list of event losses, frequency. Some of them will be associated to physics-based scenarios, some other will be associated to standard ground motion models. And finally, you will get again, basically, your probable maximum loss in this kind of mixed way. Just in order to illustrate an example that it was shown exactly in that paper. This is a kind of, let's say, scholastic academic sample. We use simply the population density in the area of Istanbul in Turkey. And here you see that we were basically sketching nothing else than the Marmara segment of the North Anatolian Fault. This is the area that has been studied and already illustrated by Professor Paolucci and Professor Smezzini. So, as you know, what we can now do is essentially on the right-hand side, illustrating how they will look like return period and losses, so basically the probable maximum loss curve, if we would analyze only that specific fault in a certain range of magnitude. As far as I remember, it was something like 6.8 up to 7.4. And so we are excluding any other kind of contribution to the hazard. By the way, obviously the hazard in that area is driven by that fault, everybody knows. And if we would use only the ground motion prediction of Chu and Young's in order to produce these footprints, what we will see is the red curve. If we would use the Bray-Rodriguez-Marek 2004, probably you recall it has already been cited by Professor Paolucci previously. It's a kind of worst case scenario of ground motion prediction equation because it's collecting only a data set of near field observation with pulse evidence and directivity evidence. So this is really kind of, let's say, worst of the worst of what has been observed. And nicely, you will see that the only footprint, so I'm not mixing any more ground motion prediction equation with footprint. This is only based on the scenarios that have been modeled in the frame of this cooperation with Polytechnic of Milan. You will see the black curve. Now, what is, in my opinion, extremely interesting is that at the beginning, it's even slightly lower than what you will get from Chu and Young's. And then you got basically that is suddenly rising up the footprint based and landing almost on the top of the Bray-Rodriguez-Marek. Basically shows how at a certain level of magnitude the fault will affect most likely over proportionate to what a standard ground motion prediction equation would say that area. Now, this is an example. Let me just stress some conclusion. This slide was already illustrated in terms of the speed dataset. And what to me it's really important to observe is that there is a serious effort, at least from the people that I'm very much in contact with, so Polytechnic of Milan, but I see also elsewhere worldwide, to not only simulate and then provide papers, but also to just publicly offer this kind of results in order to allow others to use these events and also to make comment and to understand what parts are good, what parts are not good, And this to me is extremely important because if I can tell you the status quo that I see right now in our kind of field is that obviously we are largely dominated by ground motion models in order to provide this footprint. Actually, if we look at the sensor, so the seismometer that we are looking, it's rather a sparsely worldwide sensor network. And finally, if we also take a look at the losses, what we see is that in many cases, we have access only to aggregated kind of losses. So my hope is that in the future, thanks to the scientific community, there will be a further possibility to use physics-based scenarios. These in the sense of just having stored in some kind of common database with a certain common format. I sincerely also believe that increasing the number of sensors clearly will dramatically improve the capabilities to understand if our physics-based scenarios are performing good or not. And in that respect, I must say that I see the chance, also thanks to private company, like for example SafeHub, that is installing this kind of devices. And finally, obviously, our sector is responsible to get as detailed information as possible about the losses. So all in all, and this is basically my last slide, what I want to say is that I think that in the whole community, it would be extremely beneficial to get certain kind of standard and the possibility to download these physics-based scenarios done by different institutions, most likely with different code, with different technique. But this is extremely important in order to advance in the use of these kind of scenarios. And with that, I thank you everyone, and that's it.
Thank you, Marco.